kiddos, today we're going to talk about conformers and conformations. And what conformations are is if we take a simple organic molecule like our ethane here, and I've got one drawn on the board, but I've also got a model here because I think seeing some of the three-dimensionality really helps when you're doing this, because conformers are essentially all about three-dimensionality. What a conformation is, or what conformers are they represent the fact that around this single bond between these two carbons here, I can rotate this and get this molecule that has the same formula. So everything's attached in the same place or anything. There's no stereoisomerism or anything like that going on here. But rather what's going on is there's essentially an infinite number of positions that I can rotate around this single bond. We can rotate freely around a single bond. We'll see later when we talk about alkenes and alkynes that we can't rotate around double bonds or indeed rings. We can twist them, but we can't really rotate. Well, again, that's going to be important to us. But we can rotate around this, and what this means is that if we take a molecule that looks like this, so this is our ethane. This is like sort of the simplest example of that. We've got an ethane here. We've got a hydrogen sticking up, one sticking down, coming at you, coming back at me, other way, okay? That if we can set this up in such a way that we can arrange this in ways that are more energetically favorable than in other positions, and that's what conformers are. Conformers are essentially different positions around the single bond. And so what we're looking for are conformations that are the most energetically favorable. And of course, what that means for us in chemistry, energetically favorable means lowest possible energy. A higher energy state is less favorable. A lower energy state is more favorable. So to get there, and to talk more about conformers, particularly with some of these smaller molecules, we're gonna look at a couple of things that have to do with different ways that we can draw these. And so this is our sort of classic wedge and dash model, where I didn't just draw it the way that we might have initially drawn our ethane, which would have been, I've got two carbons and I've just got my hydrogens there. Okay, back in Chem 1, you may have drawn your ethane like that. And then of course, if we were drawing a line structure, it just would have been a line, right? But what this shows is the three-dimensionality of where the hydrogens are at. And sometimes we don't think about that, but that really matters as far as our energy considerations. Okay, so normal model, line structure, this is our wedge and dash model. What this is called a sawhorse model. And a sawhorse model is useful because it's going to give us a good way to look at things to get our Newman projections, which are the model that we're really interested in this case. And so what a sawhorse model is essentially is that I've got my molecule here, okay, I've got my ethane, okay, and that what I've done is I've rotated it 45 degrees, okay, so sort of down here so that I can see the angles a little bit more, and you can sort of see where all the hydrogens are going there, okay? And what that's going to allow us to do is that it's going to give us sort of an angle to sort of eyeball this thing. And so I'm going to take my ethane here, and I'm going to bring it over, and I'm going to sort of adjust it so that it's going towards my eyeball. And so what a Newman projection is going to be is that I'm going to be looking straight down the two carbons. And indeed, anytime you're doing a Newman projection, and again, we're going to draw one here in a second, we'll see what it looks like. Anytime you're drawing one of those, you're looking straight down two carbons, okay? And then you're going to look at what's in the front and then what's at the back as well. Now, what does that Newman projection mean for you then? How are you actually going to draw that? Well, again, look at it as though you're looking dead on, okay, down the two carbons there. And in this case, we've only got two carbons, so it makes it really easy to guess what you're looking at. But so if I put that up there, you're looking at these two carbons, and so there's your front carbon, and you can't see the back carbon, okay? You're going to assume that it's there in a Newman projection. But what you can see are the things that are sticking out from that back carbon, which in this case are hydrogens, and obviously if we had a more complex molecule, would be a lot more than those hydrogens. So keeping in mind that you're looking dead on that carbon, this is what a Newman projection is going to look like. You're going to draw a circle. Essentially what the circle represents is the back carbon. Okay, and you'll see why that is here in just a second. Okay, and then I'm going to draw, in my case here, I'm going to draw this out like this. And it doesn't have to be this way. That could be inverted or in any other way. But let me tell you what this represents and show you what this is that the yellow spot here on my diagram is representing this. So I've got hydrogen, and I'm going to draw the hydrogens in here in a second. So this is where this hydrogen's going, this hydrogen, and this hydrogen. And then the space right here in the middle, that represents my foremost carbon, the carbon that's in the front. So I'm going to go ahead and draw that there this time. But remember that you don't actually you're not going to see that, right? You're not going to see a C there. You're just going to draw that symbol there. And I'm going to go ahead and put my H's on there so you can see where all that stuff is. Okay, so that's the front carbon. Remember that I said that the circle is the back carbon. And so again, if we look at our model here, remember what we're seeing in the back carbon. Let me make this to what we had. Okay, so that's the front carbon. Everybody can see that. The back carbon, of course, what it looks like is that we've got a hydrogen coming down and then one's coming up sort of in between the other ones. And so we're going to draw that like this. And we're sort of making the assumption here that the circle is representing our back carbon. And so this gives us something to draw off of all of the rest of the stuff. So those are my hydrogens there. So if I took the C away, okay, that initial C there that I had, and we're just going to draw what would normally be in there, then we would have a Newman projection. Okay? Here's why Newman projections are so awesome and so useful to us in chemistry, is that when you're looking down any two carbons and you're thinking about the rotation around that single bonded carbon-carbon pair, I can use a Newman projection to really accurately represent what's going on with all of the things that are hanging off of those carbons, with everything else in the molecule. Now this could be a 10-carbon chain, and so some of the parts of the chain could be hanging off, and I might be looking at the middle carbons, and we're going to see a more complicated one in the next video. But here's why this really matters. Remember that what I said, that why this was important, is because there's energy considerations here. There's a more stable conformation, or more energetically favorable conformer. There's a more energetically stable conformer here that can be had. So this is the sort of the model that I gave you to begin with. And if you can imagine this, remember we're twisting around the single bond here. I can turn around that single bond essentially an infinite number of ways. Okay? Considering that there's like an infinite number of really small angles that we could do in this circle. In reality, for us in the case of this ethane, there's really only two that really matter. And one of them is this one. Okay? And then the other one looks like this. Okay? And you can what you can see there is that the front carbon, okay, and we always know that the front carbon is blocking out the back carbon, but in this case the front hydrogens are really blocking out the back hydrogens. So what does our Newman projection look like for that then? So let's draw one of those real quick. Again, circles are not really my forte. Let's be honest, you guys have watched me do a few videos. Art is not really my forte. Okay, and so there's my initial. Okay, and in this case, and let me go ahead and put in the hydrogens just to make sure that we know what's going on here. So hydrogens. In this case, if I were to do this really accurately, I mean, I wouldn't even be able to see the back hydrogens, just like I can't see the back carbon, right? So what we do in that case then is that we just draw some dashed lines to sort of represent that says, hey, this is actually right behind the other one. And it probably would have been better had I drawn my initial yellow lines out a little bit more to make this a little clearer. So what this Newman projection represents is it represents a case where my hydrogens, where basically everything in the back carbon here is blocked out by the front carbon. Okay? That's going to give us rise to two names here for these two different projections that are going to become really important to us. And we're going to see that we're going to have some variations in those as well when we get to some more complicated molecules. But they have two names that make pretty good sense. This is called an eclipsed model because the stuff in the back carbons is essentially eclipsed by the stuff in the front carbons. Not just the carbons, but the substituents themselves are blocking the other substituents. You can't really see them if you're looking at them dead on. They're essentially perfectly blocked or eclipsed. Okay? And this model over here is what's called a staggered model. Staggered meaning that they're not blocking each other. And in fact, in this case, we'll see when we do butane in the next video that this would be a special case that we would call anti, where they're actually completely opposite directions of each other. But regardless, they're called a staggered model when they're not overlapping each other, when the substituents hanging off of those bonded carbons are not overlapping each other. Okay, so let's talk about energy considerations, because remember, that's what we said was the real heart of what we're doing here. Okay, so let's talk about our energy considerations here. First off, we need to learn a new term, and that is dihedral angle. That's what's on the x-axis here. The dihedral angle is the angle between the whatever, in our case, the hydrogens, but whatever's attached to the carbon. So the hydrogens in the front and the hydrogens in the back, what's the angle between them if we're looking at it on a Newman projection? So in this case, this is a 60-degree dihedral angle. In the case of our eclipsed form, that is a 0-degree dihedral angle. They're pretty much exactly overlapping each other. And again, there's an infinite number of spaces sort of in between them, but what matters for us in our particular case here is sort of the angles of 60 and what's going on there. So we're starting at 0. You can see at 0 we've got a really high energy, and I didn't really write down the number there, but that's 12 kilojoules per mole, which is quite a bit actually, okay, at the top. And then down here at the bottom it's essentially 0. Okay, and so where do we go to get from a high energy state down to a low energy state? Well, dihedral angle wise, okay, what happens if we rotate this, and keep an eye on this carbon, we're going to rotate it so that it's 60 degrees away, which is what we have in our staggered model. So we went from really high energy down to our lowest energy. If we rotate it 60 again, okay, let me try to put it here so you guys can see it. We rotate it 60 again, well, now we're back up to the top because we're back up to an eclipsed model. Everything's overlapping. We rotated another 60, and now we're over here to 180, and so we're back to our staggered model. This 60, 120, 180, all of that would matter a little bit more if we had something other than hydrogens. Essentially, since everything in our ethane here is just hydrogens, it essentially lends itself to there are only two positions that really matter, eclipsed and staggered. We're either at 0 or 60 or some multiple thereof. And so we're sort of oscillating between two states that really matter. So which one of these states is going to be best? Which one of these conformations or conformers is going to be the one that matters the most to us? Well, in a given sample of ethane, okay, most of it is going to be the staggered conformation. Well, why is most of it going to be the staggered conformation? Because that is the lowest energy state. Okay, molecules are more stable when they're in their lowest energy state, and so the vast bulk of any given sample of ethane, even though it's the same molecule either way, but it's going to be in the position where we've turned it so that we have the lowest energy. Now that leads us to something that really matters here as far as terminology, because the reason that this has a higher energy than this one is something called torsional strain. Also, I might note that this dihedral angle is sometimes called the torsional angle too. Torsion, remember, if you're thinking about physics terms, sort of means twisting or turning. And so that's the same thing that we've got here. It's called torsional strain because we're at a high strain position here because of these hydrogens. Now get this, and this is important because we're going to talk about another kind of strain in the next video. It's not like these hydrogens are like physically constraining each other, like they're bumping into each other. That's a different kind of strain that we'll talk about in the next video. But rather, what scientists think is going on is that essentially it's not really that the atoms themselves are bumping into each other, but rather that we've got a molecular orbital situation here, right? And so all of the bonding orbitals for this side and for this side, they're essentially sort of running into each other, the bonding orbitals themselves. And if we turn it so that we're at 60, then what we have is the bonding orbital here and then an anti-bonding area over here, and they just sort of fit together a little bit better. And since we've got essentially a 12 kilojoule per mole, and we've got 3 interactions between the hydrogens, we can probably say that our torsional strain here from the hydrogen to hydrogen is probably about 4 kilojoules per mole. And that's a substantial amount. That's enough to make it want to want to really favor the staggered state. Okay, and so that's torsional strain. Torsional strain, at least, is posited, and this is sort of a recent development as we've studied a little bit more in the past 20 or 30 years. But it's always been called torsional strain. We know that it's more strain, more constrained, more strained, higher energy state if they're overlapping each other here. And it's not because they're bumping into each other. That's a different kind of strain that we'll talk about in the next video, because in that video you'll be able to see that there actually is sort of some atoms bumping into each other. All right, so that's the basics of conformers and Newman projections. We're going to make this a little bit more complicated and talk about a sort of more important models and a little bit of variation in our energy when we talk about butane in the next video. Thanks, kiddos.